I know, guys, crazy things do happen. So on the screen, there's something we might have never imagined, right? So there's this operator d over dx in the exponential of e, right? And that's again a big operator which is operating on f(x). And the result is something really simple, just f of x plus 1. And this is actually true, guys. So I'm even gonna give an application to an infinite series where you can use this property to find the value of an infinite series, and that actually works. You can actually numerically verify it. I have done that. And so I've already made some bullets to decide how this video will go, right? So first of all, I will discuss what do these things like e to the power d dx, even like sine of d dx, log of d dx, what does that mean, right? What kind of operators they are. And then I will just also disprove this statement that's on the screen right now. And then we will see a quick interesting result, and then we will see an application. So I definitely think this is going to be a really interesting video. Let's begin. So first of all, let's talk about e to the power d dx. So how this works is, it works almost like an infinite series, right? So this operator is just defined as sum from n equals to 0 to infinity of, now instead of being nth power, it's just nth derivative, right? So nth derivative of like some function if there is over here, right? Divided by n factorial. So this is how it works. So let's say over here, let's quickly go over if this was, let's say, if this was a function of, let's say, f of x, then it would just have been sum from n equals to 0 to infinity, 1 divided by n factorial, and then nth derivative of the function. So that's how it would have worked. So which would basically be sum from n equals to 0 to infinity, and then nth derivative of x divided by n factorial, right? So that's how it works. So similarly, if you want to know how this operator sine of d dx works, so this is also just sum from n equals to 0 to infinity of, let me write it in the expanded form, that's more convenient. So first of all, just the single differentiation operator, right? And then minus the cube differentiation operator divided by 3 factorial, and you know the pattern, right? It's the same for log as well. Just use the infinite series. Like first of all, x, right? And then minus x squared by 2, right? X minus x squared by 2 plus x cubed by 3, and it goes in. You know the pattern, you know the sequence. Yeah. Okay. So now that we know how these operators work, so let's quickly prove this statement, and then we will be able to use it in different interesting results. So to prove this, we want to prove that this thing over here, e to the power d of dx operator, and then here as of this operator acts on f of x, this equals to f of x plus 1, right? So we know this LHS, this is defined as sum from n equals to 0 to infinity of the 1 over n factorial and then nth derivative of f of x, right? So this is just sum from n equals to 0 to infinity of 1 over n factorial of the nth derivative of x, right? So we want to prove that this is equals to f of x plus 1. So to do that, I will take a slight detour. So let's say uh, I have this function f of y, which I want to evaluate at x, right? So if I want to do that, if I use Taylor series, then this becomes f of y is equals to sum from n equals to 0 to infinity of the nth derivative of f of y, right? But evaluated at y equals to x, because okay, because okay, wait, with the instead of evaluate, this is the wrong word. With okay, I should say I have this function which I want. Okay, wait, this is wrong phrasing. Let's say I have this function f of y whose Taylor series around y equals to x, I want to find out. Okay, now this is a good phrasing. Okay, so let's say I have this function f of y whose Taylor series around y equals to x, I want to find out, right? So if I say that, then this will just be the derivative which should be evaluated at y equals to x divided by n factorial, right? And there should also be y minus x to the power n term over here, right? So we evaluate this nth derivative at y equals to x, and that becomes sum from n equals to 0 to infinity of this nth derivative 8x, right, by n factorial y minus x to the power n, right? Now, if you substitute y is equals to x plus 1 over here, so what do you get? You get f of x plus 1 is equals to sum from n equals to 0 to infinity of this nth derivative at x by n factorial, and it's just 1 to the power n, right? So that turns out to be sum from n equals to 0 to infinity of this nth derivative at x by n factorial. So that's exactly what we had earlier. So this is equal to f of x plus 1. So now this is proved. This was a pretty easy proof, even though we need a slight detour and some trick, right? So now that we have this, we will prove these two interesting results. The first one is pretty simple. To prove the first one, we just need to take this operator on e to the power x. And if you do that, we will just have this infinite sum of nth derivative on e to the power x, which is then divided by 1 over n factorial, right? Yeah. And which is then divided by 1 over n factorial. Oh, now we know that like any derivative of e to the power x, it's just e to the power x, right? So this sum becomes sum from n equals to 0 to infinity of e to the power x divided by n factorial. Now, since this sum is in the world of n, e to the power x just escapes out of the sum, and we have sum from n equals to 0 to infinity of 1 over n factorial. We know the sum is just the sum of e, right? So this is just e. That gives us e to the power x plus 1, right? And this also verifies the formula, as well as this is an interesting result in itself, right? Like this interesting operator applied to e to the power x is just e to the power x plus 1. This is both verification and interesting like formula. Now we go to the interesting application that I mentioned in the beginning, and this is also really powerful like application actually. This infinite series, which like really we don't really have any idea to sum up, is actually pretty interesting. I mean, there could be other ideas there as well, but like this one seems pretty easy to do. Okay, so if I use the same formula using f of x equals to sine x, right? So e to the power d dx of f of x, we know this should be f of x plus 1, right? That means e to the power d dx of sine x should be sine of x plus 1. And then if we use the definition again of e to the power d over dx, this is just sum from n equals to 0 to infinity of nth derivative, right, of sine x is equals to sine of x plus 1. And if you just sum up the nth derivative, and we also have 1 over n factorial, I forgot that, because over here, basically e to the power d over dx, and like nth power divided by n factorial, right? Yeah. So now, then, if you just find the nth derivative of sine x, and then to do the sum, you have sine x divided by 0 factorial plus cos x divided by 1 factorial minus sine x divided by 2 factorial minus cos x divided by 3 factorial plus sine x divided by 4 factorial plus cos x divided by 5 factorial, and so on. The sum is just sine of x plus 1. I did take this by substituting x equals to 1, and it worked. You can also take it, and like the way it's proved, like using this insane thing, I mean, like, we don't even like think like we can define it this way, but we can actually do, and then we can derive some formulas that in the work, right? I mean, this is pretty like interesting to me. I think it is to you as well. And I hope you enjoyed the video. Thanks for watching. If you did like this content, do share with your friends and let them know that there's a thing like that. That's all, and I look forward to seeing you in the upcoming videos too.